In this lesson, we are going to be continuing with the concept of equation of a plane, and specifically, we are going to be looking at the form r.n is equal to d, and also the Cartesian form of the equation of a plane. Now, I'd want you to consider a plane, and let's have a line that is perpendicular to the plane, which I'd want to call n. Now, we know that a line perpendicular to the plane is called a normal, so it's a normal to the plane. And let's say this normal meets the plane at a point A. We also want to have another point on the plane, which is the point R. Now we know that the normal to the plane N should be perpendicular to the line AR. And we also know that perpendicular vectors have their dot product equal to 0. So we're saying AR dot N should be equal to 0. Now we know that we can get AR by OR minus OA. So it's OR minus OA dot N is equal to 0. Now we can represent OR by R and OA by A. So it's R minus A dot N is equal to 0. And expanding the bracket, we'll be getting R dot N minus A dot N is equal to 0, which basically gives us R dot N is equal to A dot N. Now, A dot N is a constant, so I'll say let A dot N be equal to a constant D. So eventually, we'll be having R dot N is equal to D. And therefore, this form R dot N is equal to D is another form for the equation of a plane. You need to note that D is a constant, and it also determines the position of the plane. So if N is a unit vector, D is the perpendicular distance of the plane from the origin. So this is very important for you to note. Now we also have the Cartesian form of the equation of a plane. So if you have R dot N is equal to D, you need to know that R is just a general point on the plane. That's X, Y, Z. And we know that N is the normal to the plane. So let N be equal to the vector AI plus BJ plus CK. So since R dot N is equal to D, we can have XYZ dot ABC equal to D, which eventually gives us the Cartesian form, which is AX plus BY plus CZ is equal to D. So this is the Cartesian form of the equation of a plane. So in general, for a plane passing through a point A of coordinates x1, y1, and z1, with the normal to the plane being the vector ABC, we can have the equation of the plane in Cartesian form as A of x minus x1 plus B of y minus y1 plus C of z minus z1 equal to 0. So this is again important. Let's look at this example here. A plane contains the points A of coordinates minus 2, 1, 4, B of coordinates 1, minus 3, and 3, and C of coordinates minus 5, 6, and 0. Find the vector equation of the plane pi in the form R dot N is equal to D. So according to this question, we've got a plane and we've got these 3 points on the plane. First of all, we will need to find the direction vectors of 2 nonlinear vectors on the plane. So we are going to start by finding the vector AB. Now for the vector AB, we know that AB is equal to OB minus OA. OB is the vector 1, minus 3, 3, and it's minus the vector OA, which is minus 2, 1, and 4. So we are going to get AB as 3, minus 4, and minus 1, which I'll write as 3i minus 4j minus k. For the next vector AC, we know that AC is OC minus OA, which is minus 560 minus the vector minus 214, and this gives us the vector minus 3, 5, and minus 4, which I'd want to write as minus 3i plus 5j minus 4k. So now that we've got the two direction vectors on the plane, we can now find the normal to the plane by doing the cross product. So that'll be the cross product of the vectors AB and AC, and we can put AB on the first row and AC on the second row here, so that if we close out I, we will get the determinant of minus 4, minus 1, and 5, and minus 4, and that's of I, and it's minus. Closing out for J, we'll be having the determinant of 3 and minus 1, minus 3 and minus 4, and that's all of J, and it's plus. Closing out for K, we'll be having the determinant of 3 and minus 4, minus 3 and 5, and that's of K. Now here we'll be having the product here as 16, and that's minus 5, which gives us 21i. And here we'll be getting minus 12, minus 3, which is minus 15. And with the minus here, it becomes 15j. And here we'll be having 15 minus 12, which is 3. So we'll be having it as 3k. So we now have the normal n to the plane as 21i plus 15j plus 3k. And here it is. So using r dot n is equal to a dot n, we'll be saying r dot n, which is the normal, which is 21, 15, 3, and it's equal to a dot n. For a, I'll take any point on the plane. I'll use the point A, which is minus 2, 1, 4, and it's dot 21, 15, and 3. And for this dot product, we will get here minus 42 plus 15 plus 12, and that gives us minus 15. So in the form r dot n is equal to d, we will have the equation of the plane coming out as r dot 21i plus 15j plus 3k equal to minus 15. So that's the equation of the plane. Now let's say it was required to have the equation of the plane in Cartesian form. So we'd simply take the equation of the plane we got, which is r dot 21i plus 15j plus 3k equal to minus 15. For r, that's xyz dot 21, 15, 3, and it's equal to minus 15, which will give us 21x plus 15y plus 3z equal to minus 15. And that'll be the equation in Cartesian form. Now, if you were to use this formula here, which I gave you earlier, which requires us to have the normal to the plane, which we already have, and a point on the plane, where in this case I'll use the point B, we can substitute that into this equation so that we get 21 of x minus 1 plus 15 of y plus 3 plus 3 of z minus 3 equal to 0, which simplifies to 21x minus 21 plus 15y plus 45 plus 3z minus 9 equal to 0. So here we'll be having 21x plus 15y plus 3z, and for minus 21 plus 45 minus 9, we are going to get 15. So that's equal to 0. So we can have the equation of the plane in Cartesian form directly as 21x plus 15y plus 3z is equal to minus 15. And that's the equation of the plane in Cartesian form. So that's how else we could have done it. And that's it for this lesson.